The future we lost. Back in the 70s, NASA engineers were one step away from creating a machine that would have changed the rules of the game in the air forever. But this project, which was supposed to be a triumph, turned into one of the main mysteries of aircraft construction. Friends, meet the Sikorsky S-72, a helicopter that dreamed of becoming an airplane. What made the US military in 1988 suddenly put a definitive end to this highly classified project? What unique technologies developed specifically for the S-72 still have no analogs in the world? And what fatal miscalculation prevented the most advanced version of this transformer from taking off? The Sikorsky S-72 is not just a failed experiment, but a real artifact from an alternative reality where aviation took a different path. Watch this video to the end. We will break down the unique design of the virtual wing and try to understand why this remarkable machine remained grounded. Let's begin. There are things that look like a solution, but are actually a compromise. A helicopter is exactly such a thing. It can do what no airplane can: take off vertically, hover in place, and land where there is no runway. This is not just convenient, it is a fundamentally different way to fly. When helicopters entered mass practice in the mid-20th century, it seemed that aviation had found an ideal tool. But this tool had a ceiling, a literal one, not of altitude, but of speed. A classical helicopter, for all its advantages, is physically unable to fly faster than approximately 400 kilometers per hour. And it is not a matter of engine power. You can install an engine twice as powerful, and the result would not change. The problem lies deeper, in the very principle of rotor operation. Here is how it works. The main rotor rotates. One of its blades at any given moment moves forward, in the same direction the helicopter is flying. The other blade at the same moment moves backward, against the direction of flight. This happens constantly, with every rotation. Now add the speed of the helicopter itself. The blade moving forward adds two speeds together, the rotational speed and the helicopter speed. It moves very fast. The blade moving backward, on the contrary, subtracts the flight speed from the rotational speed. It moves slowly. The faster the helicopter flies, the greater the difference between the two halves of the same rotor. This is called dissymmetry of lift. The left half of the main rotor creates more lift than the right, or vice versa, depending on the direction of rotation. The helicopter begins to roll. Engineers found ways to compensate for this roll by changing the angle of the blades at each point of rotation. This is complex mechanics, and it works, but only up to a certain speed. As the helicopter accelerates further, a second problem arises. The blade moving forward travels so fast that the air around it begins to behave unpredictably. It approaches the speed of sound. It does not reach it, but it comes close. At these speeds, aerodynamics change, shock waves appear, lift drops, and severe vibration occurs. Simultaneously, the retreating blade slows down so much that the airflow over it begins to stall, and it stops generating normal lift. Both problems occur at the same time, and both are consequences of the same fact. A main rotor cannot be fast and efficient at the same time. Engineers had been facing this since the 1950s. By the late 1960s, it became clear. If we want a helicopter that flies fast, truly fast, at the level of an airplane, we need either to fundamentally redesign the main rotor or find a way to get rid of it. The second option sounded like science fiction. But it was precisely this option that became the starting point for what we are talking about today. By 1970, the National Aeronautics and Space Administration of the United States of America, NASA, and the US Air Force decided it was time to stop theorizing. They needed a real flying machine to test these ideas, not a mock-up, not a laboratory test rig, but a real helicopter that could take to the air and show whether the theory worked. In December 1970, a competitive bid proposal was issued, and this is where the history of the Sikorsky S-72 begins. In December 1970, the National Aeronautics and Space Administration and the US Air Force published a request for proposals. Its essence was simple. They needed an aircraft that can do everything a helicopter can: vertical takeoff, hovering, landing in restricted spaces, but at the same time flies like an airplane, fast, far, and economically. They wanted to understand if this was possible at all, and if so, how. This was not an order for a production aircraft, it was an order for an answer. Such assignments in aviation are called research programs. The goal is not to build something that will go into mass production, but to learn which direction makes sense to pursue. Money is invested in knowledge, not a product. Two major helicopter manufacturers in the U.S. responded to the competition. The first was Bell Helicopter, a Texas firm with a reputation as innovators. In the 1950s, Bell had created one of the first mass-produced helicopters to reach the military in large numbers. Bell had also experimented with tilt rotors, aircraft whose rotors tilt to act either as helicopter rotors or airplane propellers. The company knew how to push beyond standard solutions. The second participant was Sikorsky Aircraft, a Connecticut firm founded by Russian immigrant Igor Sikorsky, which by 1970 was a symbol of American helicopter design. It was Sikorsky's design bureau that built the world's first practical mass-produced single-rotor helicopter in 1939. By the time of the competition, the company had dozens of models behind it and a reputation as a manufacturer of reliable, well-engineered machines. Both participants understood the task, had the resources, and wanted the contract. The competition task involved creating the Rotor Systems Research Aircraft, abbreviated as RSRA. It was under this abbreviation that the program entered history. The task of the RSRA was unusual, even by the standards of research programs. The aircraft was not just meant to fly on its own, it was to serve as a platform for testing various rotor systems. In simple terms, engineers wanted a helicopter on which they could mount any experimental main rotor, take it into the air, and see how the system behaved in real conditions, not in a wind tunnel, not on a test stand, but in the sky. This demanded very specific characteristics from the design. The machine had to be stable on its own so that the behavior of the experimental rotor system would not be confounded by problems of the platform itself. It had to be capable of flying in different configurations, with and without the main rotor. And it had to be safe enough for the crew to work on board under non-standard conditions. Sikorsky proposed a solution that, at first glance, looked conservative. The basic design of the S-72 relied on proven components. The fuselage was based on the production Sikorsky S-71 helicopter, a widely known machine that by then was operated in both civil aviation and the armed forces of several countries. This provided a clear, predictable foundation. But then came the interesting part. Sikorsky proposed making the machine modular. The main rotor could be removed, the tail rotor could be removed, wings could be attached to the fuselage, and additional engines could be installed on the wings. Each element was a separate block, mounted or demounted depending on the test objective. This was not just a single helicopter, it was a system. Bell proposed its own concept. The details of the competitive proposals are still partially classified, but the key fact is that the committee chose Sikorsky. An official contract was signed, and funding from the U.S. military budget was allocated. The company was to build not just one, but two flight test vehicles, both for testing, both for different programs. This is where the story of the S-72 begins to differ from dozens of other research programs, because these two specimens lived very different lives. The first one flew, the second almost did not. Yet it was the second that proved to be the most ambitious, but that was still far off. First, they had to build the machine. At the Sikorsky plant in Stratford, Connecticut in the early 1970s, the engineers received the task and the money. Now they had to make the decision that would determine everything else, where to start. In aviation, there is an ironclad rule. When designing an experimental machine, you never complicate everything at once. If you want to test a new rotor system, make everything else as conventional as possible. If you want to test a new fuselage design, use a standard rotor. If something goes wrong, you must know exactly what failed. If everything is new at the same time, you know nothing. This is why the basic S-72 looks so ordinary. The fuselage of the production Sikorsky S-61 helicopter was chosen as the basis. It was a workhorse of American aviation, a large twin-engine helicopter that had been in operation for over a decade in various conditions. Its design was thoroughly understood, and its behavior in the air was predictable. Engineers knew how it reacted to every maneuver. It was the perfect foundation. However, the fuselage was significantly modified, not on the outside, but structurally and internally. The structure was reinforced at several key points because, in the future, various experimental systems, wings, auxiliary engines, and non-standard rotors were planned to be attached to this fuselage. Each change would create new loads, and the fuselage had to withstand them. The main rotor was taken from another Sikorsky helicopter, the S-71A, a 5-blade rotor with well-studied aerodynamics. The tail rotor was also standard from the same family. The engines were two General Electric TF34-GE-2 gas turbine engines, each delivering about 4,000 horsepower. For helicopters of that time, this was very serious power. But the main feature of the S-72 design was not what was installed in it, but what could be removed from it. The main rotor was attached to the fuselage via a special node that allowed it to be dismantled. The same applied to the tail rotor. Attachment points for wings were provided on the sides of the fuselage so they could be installed or removed. Mounting nodes for auxiliary engines were pre-engineered under the fuselage and on the future wings. In an analogy, it was not so much a helicopter as a construction set, like a Lego set where the basic platform remains the same and everything else changes depending on what you want to test. Except instead of plastic parts, these were aviation systems worth millions of dollars. And instead of a playroom, they had the sky over California. 2 units were built. The tail number of the first was 741, and the second was 740. In documents, they were simply called the first flight specimen and the second flight specimen. Assembly took several years. This was not due to slowness, but thoroughness. Every component was documented, and every decision was justified, because these machines were meant to be a source of data, not just fly. In the autumn of 1976, the first flight specimen, tail number 741, was ready for flight. Tests took place at Sikorsky's factory airfield in Stratford. The first flight was nominal. The machine behaved predictably, which was exactly what was required. No surprises, no unexpected behavior, just a large, stable, controllable helicopter. This was the success because the task of the basic S-72 was not to surprise, but to give engineers confidence that the platform worked, was stable, and could be relied upon. Only after verifying this could they move forward. The machine reached NASA only in 1979. The 3 years between the first flight and the transfer to the agency were spent on additional tests, refinements, and addressing issues, standard procedure for research programs of this level. In 1979, the first specimen arrived at the NASA Ames Research Center in California, one of the primary testing grounds. This is where the next stage began and where the program stopped being boring because engineers finally obtained what they wanted from the start, a stable platform that they could now begin to modify significantly in ways no one had modified a helicopter before. The first step was the wings. Why does a helicopter need wings? At first glance, this is a strange question. A helicopter is a helicopter precisely because it does not need wings. The main rotor creates the lift that keeps the machine in the air. An airplane wing does the same, but differently. It is fixed and works only when the machine moves forward fast enough. But here's where interesting mechanics begin. When a helicopter flies horizontally and accelerates, the main rotor continues to create lift, but it also creates drag. A large rotating disc above the fuselage is not the most aerodynamic design. The faster the helicopter, the more energy is wasted simply pushing this disc through the air. Now consider another scenario. What if a fixed wing takes over part of the lift? The logic is that at cruise speed, the wing generates a significant portion of the lift. The main rotor is unloaded, so it does not need to operate at full power. The pitch angle of its blades can be reduced. A smaller angle means less drag, and less drag means higher speed. This is not theory. This principle worked on several experimental aircraft back in the 1960s, and it was decided to test it on the S-72. Small but fully functional wings were added to the first flight specimen, tail number 741. They were attached to the sides of the middle part of the fuselage. The span of each wing panel was relatively modest, as the designers did not want to overload the fuselage and disrupt the machine's balance. The wings were designed specifically to unload the rotor, not to replace it completely. 2 turboprop engines were installed on these wings. A turboprop engine is not a jet engine. It works differently. Inside, there is a gas turbine that burns fuel and creates hot gases. But these gases are used not to create direct jet thrust, but to rotate a shaft which turns a propeller, much like a conventional piston engine turns a propeller on a classic airplane, only more powerful and efficient at high speeds. Why turboprops and not jets? We will talk about this later. there is a separate and highly illustrative reason. For now, let's remember the main point. 2 additional engines on the wings were supposed to push the machine forward, while the main rotor, unloaded by the wings, rotated at lower blade angles of attack. Theoretically, this allowed for speeds exceeding 560 kilometers per hour. For comparison, most production helicopters of that time had a cruising speed of around 220,250 kilometers per hour. Reaching 560 would have been a major advancement, the speed of a small turboprop airplane, while retaining the ability to hover in place and land without a runway. The tests began, and it quickly became clear that theory and practice diverged. The first problem was balance. When the wings take on a significant share of the lift, the center of pressure shifts. The main rotor and the wings generate lift at different points. At low speeds, the rotor dominates and everything is fine. At high speeds, the wings contribute more and the machine behaves differently. Pilots felt the control characteristics change depending on speed. This was not a catastrophe, it was a complexity that needed to be studied and described. The second problem was more fundamental. By adding wings and turboprop engines, engineers got a machine that combined 2 different ways of generating lift and thrust. But these 2 methods were not optimized for joint operation. The main rotor was designed as the primary system, and the wings were added as an auxiliary one. At a certain point, they began to interfere with each other. The airflow from the main rotor pushed downward, which is normal for a helicopter, but it also pressed down on the wings from above, creating additional pressure not accounted for in the calculations. In response, the wings affected the airflow pattern around the lower part of the main rotor. The 2 flows interacted unpredictably. The target of 560 kilometers per hour was not achieved. The exact data on the maximum speed shown by the S-72 in the winged configuration with turboprop engines remain partially classified, but the key fact is that the target indicator was not reached. The program obtained valuable data on the interaction of rotor and wing systems, which was the real goal, but the speed question remained open. Then, someone in the design bureau asked a question that changed the direction of the entire program. What if the problem is not how we combine the rotor and the wing, but that we are trying to combine them at all? What if the rotor and the wing should be the exact same thing? In aviation, there are ideas that, at first acquaintance, sound like a mistake. Not like a bold solution, not like an unconventional approach, but precisely like a mistake, something that clearly contradicts common sense and basic knowledge of how flying machines operate. The X-wing idea was exactly like that. Its essence can be formulated in a single sentence. The main rotor of a helicopter accelerates, lifts the machine into the air, and then stops, right in flight, and after stopping, it becomes a fixed wing on which the machine continues to fly. If you are thinking, wait, that's a catastrophe, you are thinking correctly, because that is exactly where everyone who heard about the X-wing for the first time started. Let's look at why it was not a catastrophe and why it could work at all. Let's start with the shape. A conventional main rotor blade is a wing, not metaphorically, but literally. In cross-section, its shape is identical to an airplane wing, rounded on top, flatter on the bottom. This shape is called an aerodynamic airfoil. When air flows around it, an area of low pressure is created above the blade, producing lift. When the rotor rotates, each blade moves through the air at high speed, creating airflow around the airfoil. The blade works as a wing precisely because it moves. Now the question is, what happens when the blade stops? On a conventional helicopter, this leads to a catastrophe. Lift disappears and the machine falls. But the X-wing had a different plan. When the rotor stops, the blades lock in a fixed position. The 4 blades form the shape of the letter X, hence the name. 2 of the 4 ends point forward and 2 point backward. At this moment, the machine moves forward with sufficient speed, like an airplane, and the air flows around the stationary blades just as it flows around the wings of an airplane. Thus, the blades continue to generate lift, no longer through rotation, but due to the forward speed of the entire vehicle. This is a fundamentally important point. Lift is always the result of air moving relative to an aerodynamic airfoil. It does not matter whether the airfoil moves through the air or the air moves past the airfoil, the physics are the same. But here, the next question arises. An airplane controls lift mechanically, using flaps, ailerons, and rudders. It deflects parts of the wing, changing the airflow pattern. On the X-wing, the blades were rigid and stationary, with no mechanical control surfaces on them. How, then, do you control lift? This is where the true heart of the X-wing concept lies, what made this idea not just bold, but revolutionary. Lift control on the X-wing was performed using compressed air. Channels were laid inside each blade. Compressed air from the engines was supplied through these channels. On the leading and trailing edges of the blade, there were narrow slots, nozzles. Air was blown outward through these nozzles in a thin jet precisely along the blade's surface. What happened next is pure aerodynamics. The jet of air blowing along the surface did not detach from it, but adhered to it and bent the main airflow around the blade. This phenomenon is called the Coandă effect, named after the Romanian engineer Henri Coandă, who described it. The bent flow behaved as if the blade had changed its curvature. Lift changed without a single moving mechanical part. If you want more lift on one side, you add air through the corresponding nozzles. If you want less, you reduce the supply. If you want to change direction, you redistribute the flow between the leading and trailing edges. This is called circulation control of lift. Essentially, these are virtual flaps, flaps without mechanics, flaps made of air. All of this happened simultaneously on 4 blades, at multiple points on each blade, in real time. The air distribution was managed by a special computer system, very complex by the standards of the early 1980s. Now about the transition. The change from helicopter mode to airplane mode was supposed to look like this. The machine takes off vertically, with the rotor spinning and acting as a normal main rotor. The machine gains horizontal speed. At some point, the speed reaches a value where the stationary blades are already capable of generating sufficient lift on their own. At this moment, the system issues a command. The rotor speed begins to decrease in a slow, controlled manner. The computer simultaneously increases the air supply through the nozzles, compensating for the drop in lift from the slowing rotor. At some point, the rotor stops completely and the blades lock in the X position. The machine continues to fly, now as an airplane. This transition from helicopter to airplane right in the air, without landing, without manual reconfiguration, was the main promise of the X-wing, and that is why the program received substantial funding. But the more complex the idea, the more things can go wrong. Let us try to understand how this worked in practice, without formulas, just through physics you can feel. Take a sheet of paper. Hold it horizontally by one edge in front of you. The free end sags downward. Now, blow over the top surface of the sheet along it. The free end rises. You did not push it from below, you created an area of low pressure above it, and the atmospheric pressure from below lifted the sheet. This is lift in its simplest form. Now, let's make it more complex. Take the same sheet and bend it slightly to give it curvature, like an airplane wing. Blow over it again. The lift will increase because the curved surface forces the airflow to travel a longer path over the top, reducing the pressure even more. The greater the curvature of the airfoil, the greater the lift. On a conventional airplane, flaps are used to change the wing's curvature. These are mechanical surfaces that deflect downward and physically change the shape of the wing. More curvature means more lift. Everything is clear and mechanically simple. On the X-wing, there were no flaps at all. The blade was rigid and stationary. Instead, they used the Coandă effect, the one we discussed. Here is exactly how it worked. Along each blade, inside it, 2 longitudinal channels were laid, one along the leading edge and a second along the trailing edge. Air tapped from the engine compressors was supplied under pressure into these channels. On the edges of the blade, there were narrow slots, literally a few millimeters wide. Through these slots, air was blown outward in a thin, high-velocity jet directed strictly along the surface of the blade. Now the Coandă effect in action. The jet of air, rushing out of the slot, does not detach from the blade's surface. It adheres to it and curves around the edge. This is not intuitive, but it is physics. The fast jet creates a low-pressure area between itself and the surface, and atmospheric pressure literally presses it against the surface. Curving around the edge, the jet pulls the main airflow around the blade along with it. The flow bends and the blade gains additional curvature, not physical but aerodynamic and virtual. The result is more lift without moving any mechanical part. If less lift is needed, the air pressure in the channel is reduced. the jet becomes weaker, the Coandă effect weaker, and the virtual curvature smaller. If you need to change the direction of the resulting lift, the air is redistributed between the leading and trailing edges. When the leading edge is more active, the flow curves around the blade differently than when the trailing edge is more active. This sounds elegant, and indeed it is, but here begins the part that explains why the X-Wing was an incredibly complex project for its time. On the X-Wing there were 4 blades. On each blade there was a leading and a trailing edge. On each edge there were several independent sections with separate nozzles. This meant dozens of independent control points for the airflow, each affecting the machine's behavior. All of this had to work simultaneously, in real time, with constant adjustments. Compare this with a conventional airplane. A classic passenger airplane has flaps, ailerons, elevators, and rudders, dozens of mechanical control surfaces. The pilot moves the yoke, and a system of linkages and actuators deflects the required surfaces. This is complex, but it follows a clear mechanical logic. On the X-Wing, instead of mechanical surfaces, there were dozens of air supply points, and each point required not just the command to deflect by so many degrees, but a precise calculation of pressure, flow speed, air temperature, flight speed, and blade angle of attack. All of this was interdependent. Changing the pressure at one point affected the flow characteristics at others. This was not a mechanical task, it was a computational task. In the early 1980s, when the X-Wing was being seriously developed, onboard computers were incomparably weaker than what is found in any modern airliner today. The programmers working on the X-Wing control system were essentially writing control algorithms for a task that was at the limit of the computational capabilities of that era. They succeeded. The software was developed. But this process in itself took years, and it was one of the reasons why the second prototype, the one with the X-Wing, remained on the ground for so long. It was not enough to build the mechanical part. They also had to teach the computer to manage it in the air. It is important to understand the era in which all of this was happening. The 1980s was an era when fly-by-wire control, where the pilot moves a lever and a computer decides exactly what to deflect and by how much, was just beginning to enter practice. This was a significant advancement. The X-Wing went even further. It proposed control not through a computer with mechanical actuators, but through a computer with pneumatic actuators, air instead of metal, pressure instead of linkage. This was so far ahead of its time that the engineers were essentially solving 2 problems at once. They were creating a new type of aircraft while simultaneously inventing the tools necessary to build it. But there was another problem, one that is not usually talked about first, a purely practical problem, and it concerned neither physics nor programming, but what happens if everything does not go according to plan? In aviation, there's an unwritten rule. The more unusual the machine, the more attention is paid to how to get out of it. This is not because engineers do not believe in their work, but because they believe in statistics. Any fundamentally new design carries unknown risks, risks that cannot be calculated in advance and can only be discovered in the air. One must be prepared for this. On the X-Wing, they took this very seriously. Let us start with the choice of engines. We have already mentioned that the wings of the S-72 had turboprop engines, not jets. This decision seems like a minor technical detail, but in reality it says a lot about the safety philosophy of the entire program. A turboprop engine creates thrust by rotating a propeller, whereas a jet engine creates thrust by expelling hot gases backward. A jet engine, all else being equal, develops significantly more thrust and allows for higher speeds. If the goal was to achieve maximum speed, it would have been logical to install jet engines, which were used on most high-speed experimental aircraft of that era. But on the X-Wing, they chose turboprops, and the reason was not cost savings or availability. The reason was the emergency system. The designers provided a mechanism for the forced ejection of the engines. In the event of a serious emergency, rotor system failure, loss of control, or critical vibration, the system was designed to operate in 2 stages. First stage, pyrotechnic charges detached both engines from their mounts on the wings and threw them away from the fuselage. They were not just shut down, they were physically jettisoned. This was necessary so that at the moment of crew ejection, the running engines would not be in the path of the ejecting seats. This is where turboprop engines had a critical advantage over jets. A jet engine, during operation, creates a powerful stream of hot gases behind it, with temperatures that can reach several hundred degrees. If such an engine is next to the fuselage during an accident, The area around it is extremely dangerous. Jettisoning a jet engine and guaranteeing a safe ejection trajectory is very difficult. A turboprop engine is significantly safer in this regard. Its exhaust is directed and less intense. After being jettisoned, it does not create unpredictable hazard zones around the machine. The second stage after jettisoning the engines was crew ejection. There were 2 crew members on board the X-Wing, both in ejection seats. The ejection system used rocket propulsion. Small rocket boosters under the seat launched the seat with the pilot vertically upward and away from the machine, after which the parachute opened. This scheme had been proven on many military aircraft, but on the X-Wing it had a specific complexity. Usually, ejection seats are designed for a specific airplane with a known geometry. Engineers know exactly what structures are around the seat and calculate the trajectory so that the pilot does not strike them. On the S-72, the geometry changed depending on the configuration. Wings could be present or not, engines installed or removed, and the rotor rotating or locked in the X position. Each configuration created its own obstacle zone around the seat. That is why jettisoning the engines was the first stage. First, clear the engines from the path, then eject the crew. This entire system, pyrotechnics, jettisoning, ejection, existed for one reason. The engineers did not know how the X-Wing would behave in the air. They could calculate and they could simulate, but real air always presents surprises that are absent in calculations. They understood this and prepared for the worst. There is something very honest about this, not panic or lack of confidence, but sobriety. The people who created one of the most innovative concepts in the history of helicopter engineering simultaneously prepared very methodically for the possibility that it might not work. This is true engineering culture. You believe in an idea and work on it to the end, but you always know where the exit is. They never had to test the emergency system in real conditions, not because everything worked perfectly, but because the second prototype, the one with the X-Wing, never climbed high enough into the air for the emergency system to be needed. This is perhaps the most bittersweet detail of the whole story. Let us reconstruct the chronology, accurately and without embellishment. In 1976, the first prototype, tail number 741, made its first flight at Sikorsky's factory airfield in Stratford, Connecticut. The machine was in its basic configuration: a standard main rotor, no wings, and no auxiliary engines. The flight was nominal, data was collected, and the program moved forward. In 1979, the first prototype was transferred to NASA. The machine arrived at the Ames Research Center in Moffett Field, California. Here, wings and 2 turboprop engines were installed. This was the RSRA configuration, Rotor Systems Research Aircraft. Testing in this configuration began. Data was collected, problems were logged, and reports were written. In parallel, work was underway on the second prototype, tail number 740, which was intended for the installation of the X-Wing system. Work on it took longer than on the first, for an understandable reason. The X-Wing required not only mechanical assembly, but also the development of software for the airflow control system. This took time, a lot of time. By the mid-1980s, the second prototype was assembled in the X-Wing configuration. The 4 blades in the shape of the letter X were installed, the channels inside the blades were laid, the nozzles on the edges were in place, the compressed air supply system from the compressors was connected, and the emergency system with engine jettisoning and ejection seats was installed and tested on the ground. The machine stood in the hangar, ready, or almost ready. The control system software continued to be refined. Engineers conducted ground tests, running the air supply system, checking channel pressures, and testing the computer's response to control inputs. All of this was done on the ground, on the apron, without taking off. Meanwhile, the first prototype continued to fly. In 1984, the first prototype made its second landmark flight, this time in a configuration without the main rotor. The wings and turboprop engines were installed, but there was no main rotor. The machine took off and flew solely as a fixed-wing airplane. This was an important step, a check of how the S-72 fuselage behaved in airplane mode without any rotor system at all. This was the third significant flight in the history of the program. After this, flight tests virtually stopped. This was not because of a technical problem or unsatisfactory results, but because of problems of a different kind, financial ones. Research programs of this scale are expensive, very expensive. By the mid-1980s, the cost of the S-72 program was measured in hundreds of millions of dollars, with funding coming from the United States military budget. The military needed concrete, measurable results, preferably in the form of a machine that could be put into production. The S-72 program provided data, vast arrays of data, reports, graphs, and conclusions about the behavior of rotor systems. All of this was valuable for science and for understanding flight physics, but it was far from mass production. The second prototype, with the X-wing, stood in the hangar and did not fly. The software was still being refined, deadlines were slipping, and the budget was growing. At some point in the Defense Department, the question was likely raised: how much longer will we pay for a machine that does not take to the air? No answer was found that satisfied the financiers. In 1988, funding for the program was terminated. The decision was administrative, not technical. No one said, the X-wing does not work, and no one recorded a failure of the concept. The money simply stopped coming. The second prototype never made a single flight in the X-wing configuration. Think about this for a second. Years of work, hundreds of engineers, a concept that could have changed the perception of how flying machines travel, a computer system developed at the limit of the air's capabilities, an emergency system thought out to the smallest detail, and a machine assembled, tested on the ground, and ready for flight, yet it never took off. After the program was closed, the first prototype was transferred to the Smithsonian Institution's National Air and Space Museum in Washington, D.C., where it remains today. The fate of the second prototype was more prosaic. It was scrapped. A machine that could have become one of the most innovative aircraft in history ended its existence as scrap metal. But what is interesting is that when the program was closed, the ideas it generated did not disappear. They remained in reports, in patents, and in the minds of the engineers who worked on it. And some of these ideas live on to this day. When a research program is closed, funding vanishes and jobs disappear. Sometimes the machines themselves disappear. But ideas rarely disappear. They go into reports that settle in archives, into patents that remain active, and into the minds of engineers who move on to other projects and take their knowledge with them. Sometimes, years or decades later, these ideas resurface in a different context, in different hardware, but with the same underlying physics. This is exactly what happened with the legacy of the S-72. Let us start with circulation control of lift, the very technology of compressed air through nozzles on the edges that was the heart of the X-wing. This concept was not born with the X-wing. It had been studied since the 1950s. But the S-72 program gave it something vital. Real data from real tests on a real machine. Not a wind tunnel, not a mathematical model, but data on how the system behaves in conditions close to operational ones. This data was partially published and entered scientific circulation. Today, circulation control of lift is actively studied in the context of fundamentally new tasks. One of them is unmanned aerial vehicles with vertical takeoff and landing, drones and air taxis that must take off like a helicopter and fly like an airplane. This is the same task that the X-wing solved, but now without a crew on board, with electric motors, and with computational power that the engineers of the 1980s could not have dreamed of. Boeing has funded research into circulation control for advanced aircraft in various years. The Defense Advanced Research Projects Agency, DARPA, has repeatedly included this technology in its research programs. The idea did not die. It simply waited for technology to catch up. Now, let us look at another legacy, the concept of a machine that flies both as a helicopter and as an airplane. In 2015, Sikorsky, the same company that built the S-72, introduced the S-97 Rotor helicopter. This is the design with two coaxial main rotors spinning in opposite directions on a single shaft, and a pusher propeller in the tail. Its maximum speed is about 480 kilometers per hour, which is significantly faster than any standard helicopter. The S-97 does not use the X-wing or circulation control, but it solves the same problem with which the entire S-72 program began in 1970, how to make a helicopter truly fast. Another example is the SB-1 Defiant helicopter, developed jointly by Sikorsky and Boeing, which also uses coaxial rotors and a pusher propeller, with a maximum speed of about 460 kilometers per hour. The program is actively developing. Finally, there's the Bell V280 Valor tilt rotor from Bell, the very company that lost the competition to Sikorsky in 1970. A tilt rotor is a machine whose rotors tilt. During takeoff and landing, they face upward and work as helicopter rotors, while in horizontal flight, they tilt forward and work as airplane propellers. This is a different way to solve the same problem, and it developed in parallel with the X-wing, partially addressing the same questions. All of these programs share one thing. They stand on the shoulders of dozens of research projects that preceded them, and the S-72 is one of those shoulders. But there is something else, something that directly connects the S-72 to the present day. In 2013, NASA published a study on circulation control of lift as applied to advanced wing configurations. In the list of references for this study are reports from the S-72 program. Data collected on that machine in the 1980s was cited in a 21st century scientific paper. This is the true legacy, not a museum exhibit in Washington, D.C., though the first prototype stands there and can be seen, and not beautiful photographs of an unusual machine, but lines and a list of references, data that continues to work decades after the program was closed. The Sikorsky S-72 did not become the future, that is a fact, but it did something else. It outlined the contours of that future, showing where the boundaries of the possible lie, where physics resists and where it yields to engineering thought, where computers cope and where they do not yet. The engineers who came after knew where to go because someone had already walked part of that path before them on a strange machine with an X-shaped wing, which stood in a California hangar and never truly took off. Sometimes the most important steps are the ones that nobody sees.